Okay, what I'd like to try today is talk about the geometry of orbits 2, talking about gravity. If you remember, the first thing was talking about the shape of the orbit around a sun or a star, which is an ellipse, where we talked about Kepler's second law. First law was that it traveled around an elliptical orbit. Second law was that as you moved farther away, you could move slower and slower. And as you move closer towards like perihelion, you got to move faster and faster. But it's an equal sweep. So if you move faster, if you drew lines from the sun out, you actually looked at the area, it'd be the same. And the third law was that you can actually calculate how far the planet is if you know how long it takes to go around, or if you know how long it takes around, you can figure out how far it is. Now we're going to talk about gravity, and gravity is the glue that holds it all together. It's the glue that binds. Newton is actually given credit for discovering gravity, but he actually didn't discover it. He's just the first one to actually quantify it, where he supposedly was sitting when he was 12, sitting under an apple tree in his hometown. He was there because the bubonic plague was driving people out of cities. He had gone to his hometown to actually stay away from it, and he's sitting under there and he notices an apple drop. Probably didn't hit him in the head, it just dropped beside him, and he'd seen lots of apples do that before, but that's the one that actually kicked him into trying to understand the idea of gravity, and he came up with his laws of motion. This is Cirque du Soleil, and Cirque du Soleil actually does a lot of things seemingly against the rules of physics, but if you're on this planet, in this universe, you have to obey it. Let me talk about the center of gravity for a second. Center of gravity is basically the center, these little red X's you see on these individuals, and you can see they're not always in the same place, but basically it's right around your belly button. Could be a little above it or a little below it, or right smack in the middle. If you actually get your weight shifted more towards the bottom, it drops a little bit. If it's more toward the top, it moves up a little bit. Center of gravity probably, or could actually be right about here where there isn't really any mass, but as long as they can keep this stuff all centered over this location, or this location doesn't, like in this individual, move past these arms, this will stay steady. Okay, gravity. If you think about gravity for a second, I got to get this a little smaller. Gravity is said to be, the force of gravity is said to be 9.8 meters per second. That means if you're on the Earth, a really quick symbol for the Earth is, especially if it's yellow, real quick symbol for the Earth is a circle with a cross through it. It actually represents the four phases of Earth: earth, wind, fire, and water. That is the symbol for the Earth. I'll talk about that again a little later, and certainly when we get into the solar system, which I think is the next thing we're going to move into. If you're in our atmosphere and you drop a feather and you drop a ball, they will try to fall at the same speed, but there's more air resistance with the feather, so it falls slower. If you actually equate this over to this location, put it in a vacuum, you take the air out, these guys would fall and hit the ground at the same time. They actually accelerate at 9.8 meters per second. So the first second they fall, actually half of this, because they're starting with zero acceleration. But then they start falling at 9.8, then that doubles, and that's going to be 19.8 and 19.6, and it just keeps doubling and doubling and doubling. Air will eventually stop that, but if you did it in a vacuum of space, you'd keep accelerating until, of course, you reached zero acceleration when you hit the planet. Gravity is attraction force between any two massive objects. So any two objects that have mass will actually have a gravitational force, regardless of where they are in the universe. It depends on two variables. Mass is the first one. It's a direct force. So if you take a look at these, you've got two balls here with the mass of m. That's one force. If you actually increase one to double that, you actually double the force. It's a direct effect. If you have 2 and 2, then you've got more mass on both sides, your force goes up to 4. And if you actually keep one at 1, raise the other one to 3, you've got a mass of 3. It's a direct effect, pretty easy to see. Second one is distance. This is an indirect effect. In other words, as distance goes up, gravity goes down. But not only is it indirect, it's also an inverse square. So, same example, you have two m's, That's a distance of 1. You've got the force of 1. You got 2 m's and you double the distance. Well, what we have to do is we actually have to square it. So we take 2 times 2 gives us 4, and we have to inverse it, put it underneath 1. So now we have 1/4 the force. If we decrease the distance by half, you have to square 2, which gives you 4, take the inverse of 1/2, which is 4, and now we have a gravity of 4. And if you take 2's, which is double that, double the distance, you still have the same force you had in this example. So, the way it works is force of gravity. You can have 0 gravity if you have 0 mass. But if you increase your mass, you increase gravity. So 100 pounds, 200 pounds, 250 pounds. So we take the mass, we increase it, we actually get more gravity. Then the force of gravity in terms of distance. If you actually have a lot of gravity and you actually increase the distance, it goes down by the inverse square. So you can see this would be like 1, and here would be like 2 for distance, and you actually get half of it, because you actually get 1/4 of it, because you square it and then you inverse it. And it just keeps going down and down. And the one thing is, no matter what, this will never get back down to 0. So you're close to it, you're 180 pounds. You're far from it, you're 151 pounds. Now let me go over to this one. This is actually a parody off of Neil Armstrong and Buzz Aldrin standing on the moon, and Buzz says, "Neil, I've lost so much mass since coming to the space." And then says, "Buzz, you didn't lose mass, you're on the moon." Basically what happens is the moon has 1/6 the mass of the Earth, so it has 1/6 the gravity. You're standing on top of it. A person who weighs, he probably weighed 200 pounds. He's got another 250 pounds. That's 450. Let's say he weighed 600 pounds with all this stuff. That's an exaggeration, but I want to do this easily. If he stood on a scale on the Earth, he'd weigh 600 pounds. Stands on the moon, he's only pulled down by 1/6. He only weighs 100 pounds. So he doesn't weigh anywhere close to 100 pounds here. His body's used to actually supporting 200 pounds. That allows him to move a lot more like a bunny. Okay, force of gravity and distance. The rocket takes off the Earth. It's going against a whole bunch of gravity, but as it gets higher and higher and higher in space, its gravitational force goes down and down and down and down and down. These are the escape velocities. If you wanted to actually escape from the Earth, you have to obtain a speed of 7 miles per second. That actually is just about the same curvature of the Earth per second. So you'd actually have to be able to move every second 7 miles across the surface. That's 25,200 miles, just about 25,000 miles per hour. If you want to do it on the sun, and this is a symbol for the sun, not 7 miles per second, that won't do it. You've got to move 384 miles per second because it is so massive. And that's 1.38 million miles per hour. Okay, if you go down here, what we have in this picture is an increase of gravity. And we have an increase of gravity because we have a density of, you look at these little red things. Density, if you remember, is how many things you have per unit volume. And you can see we have this many. Well, that's pretty consistent. But if you get to this area, maybe like an iron ore intrusion, iron ore thing, where these things are a lot more dense. If you actually counted them in this section, you'd find out there were a lot more red dots. So what happens is you drop this ball from this ladder. Let's say the ladder is 9.8 meters tall. And hopefully a physics teacher won't see this. We'll say it takes 1 second to fall. We go over here and it actually is going to fall a little faster. It's actually starting to feel these little dots. may actually fall a little slower because maybe it actually feels the root from this tree. But if you drop it here, it's going to feel the full force of that intrusion, that more massive blob. It's going to fall faster. This will feel not quite as fast as dropping it through the center, but it will drop real fast compared to this one. And then we move off and we're onto this area again. And if you take a look at the line actually moves. Starts out at being here, and then as you get closer and closer to that massive body, it goes up. And then right here, it's actually the highest, and then it starts going back down, and then it obtains about the same here as it did there. Okay, this is also going to control how objects like satellites move across the surface of the Earth. If you take a look at this one, here's the Earth again, and I'm just going to draw that symbol right there for the Earth, although I think you can see that pretty well. This is the Moon, let's say. The Moon's actually falling at a certain rate, a lot less than 9.8. The farther you get away from the surface of the Moon, remember, inverse square, the slower you fall. Well, this Moon is falling in towards the Earth, and if it actually stopped moving, and this doesn't work very well because it's moving the wrong direction, but if it stopped moving, the Moon would slam right into the Earth. If it slowed down, it would spiral in, getting closer and closer and closer until it hit. If it didn't accelerate as fast as it is, it would actually go flying off into space. What's keeping it from falling is this velocity. It's moving off to this side. And as long as it moves off to this side, it will keep moving along this orbit all the way around. But remember, it's actually moving this way. So it's moving this way around the Earth, because we want to look at it from the northern hemisphere. So it moves this way around its orbit. And as long as it can keep the same acceleration and the same velocity, it will continue to do that. A neat thing to think about, if you think about like a large building, if you had a 400-kilometer building that's 0.6 to about 230 miles tall, really tall building, and if you just got to the top and you stepped off, well, let's say you actually stepped off onto a spongy but very massive Earth, you actually landed and you go, oh, that was fun. Let me try something different. You go back up on top and you start from one end. Instead of just jumping off, you run and run and run and then jump. You find out you're going to fall the same speed, but the Earth actually falls with you, and you get to fall a little farther away. And if you went a little farther, you went a little faster, like you put rocket on the end of you and you jumped, you could actually find out, that's not drawing anything, and you can find out that you would actually go all the way to there. And if you put 2 rockets on, you would find out that you could go to there. What if you put 5 rockets on and you actually jumped and you traveled along this line? What that would mean is that you've jumped, the Earth actually falls away from you, you've jumped at the same curvature as the Earth. And as long as you can do that, you can stay in orbit. And that's what the Moon's doing. That's what satellites do. That's what you could do if you could actually be in a spacecraft. As long as you can fall, and basically all you've got to do is get to, if you start at this section right here, get to this point as you fall, travel along that orbit, and as long as you get to that point, falling that far in that angle, you'll never hit the planet. If you slow down, you will spiral in and eventually hit the planet. If you somehow got sped up, you would spiral out and eventually leave. And this is the way we get to the Moon. We go up and we obtain this speed. We stay there, we check out our systems, and then we figure out the Moon's way over here somewhere. We figure out right here we increase our jets, turn them back on, and we actually get speed, and we still are in the gravitational force of the Earth. We curve around, and then we eventually go over to where the Moon is going to be. That also affects Kepler's law. Remember, the second law said equal area? where this point right there is the same as that point right there because they're the same, but it's also the same as here. If you actually took the area of that and compared it to the area of here, it'd be the same. The planet over here doesn't have to move as fast because it's farther away from the sun. So it has a slower orbital speed when it's apo, and a faster speed when it's perihelion. Okay, it all has to do with inertia. Okay, so as long as you can keep your body going at a certain speed, you can stay in an orbit. As long as the Earth can go at a certain speed, it can stay in an orbit. Okay, this will be in the back of your Earth science reference tables. This won't be. Here are the symbols that I used: the Sun and the Earth. The Moon's got one, and Neptune's got one, and Mercury's got them, and Pluto's got it, and Mars has got it, and Venus has got it, and Uranus has got it, and Saturn's got it. They've all got their own little symbols. Pluto's doesn't make this list because, remember, in 2003 it got demoted. But if you take a look at this one right here, this is the mass. So if you actually lived on this planet, you would take your weight and you'd multiply it by 1, and that's how much you'd weigh on this planet. If you went to Venus, you could actually take 82% of your weight, and that's how much you'd weigh there. If you went here, you could take 100th of your weight, and that's what you'd weigh there. If you went to Jupiter, you really could just multiply your weight by 317 times. So you'd actually be really heavy on this planet, and you'd actually be pretty heavy on Saturn too, but nowhere close to the same. This is the way you can actually sort of calculate weights if you want to go to different places. And gravity also plays a part in suns. This is called stellar equilibrium. Sun basically has two forces. It has a force that, because of gravity, is pushing in, but it's also got a tremendous amount of heat in the center, which wants to push out. And as long as we can get these forces in and out, pressure out because of the heat, pressure in because of gravity, as long as we can get these two forces to equal out, we get what's called equilibrium. If the expansion force is larger than the gravity force, the star is going to expand. That's what's going to be in our future as the sun goes with what's called a red giant phase. And then if you can actually get more heat, what will happen is the temperature will, if you can get more heat, that's the same thing as expansion. If you can actually get more gravity, you can get, and this doesn't show it, you can get compression, and that's what happens with other stars, and happened to our star to actually make it into the sun some 4.6 billion years ago. Notice that these arrows are the same as these arrows, so we get the same thing. We get stellar equilibrium, or we get the equilibrium of stars. Okay, gravity, mass and distance. You increase mass, you increase gravity. Increase distance, you decrease gravity by the inverse square. And that explains the whole elliptical shape, and that is basically, like we said, it is the geometry of orbits. Thank you much. Bye.